Right. Hello, everyone. Can you hear me clearly, everyone?
Yes.
All right, sounds good. Yeah, thanks for the introduction. So, yeah, I'm not studying in Canada, but I'm invited by DLS, so that's why I'm here. So I've been enjoying a lot of good presentations so far and learning a lot. And today I'm gonna talk about noise contrastive estimation, which was proposed in 2010. And this work is considered to be a quite seminal work in this area of estimating unnormalized models and inspired lots of recent models like GANs and contrastive learning. Contrastive learning for representations and so on. So yeah, I hope you enjoyed this talk. And on top of this, I'm gonna add an additional personal perspective on this framework, which is based on F divergences. So yeah, so let's see how it's gonna work. So, okay, so let's start with the problem setting. So our problem throughout this presentation is gonna be the parameter estimation with unnormalized models. So we are gonna assume data generating distribution denoted by PDX. And also we assume a class of unnormalized distributions, which we are gonna denote by phi, which is a collection of phi alphas. Each phi alpha is an unnormalized model such that, and also we assume the well-specifiedness of this unnormalized distributions in the sense that there is some alpha star, parameter alpha star in the parameter set calligraphic A, such that the unnormalized version of it, the normalized version of it is actually the data generating distribution. So in other words, we assume that the class of models is rich enough so that it captures the data generating distribution. So this is a sort of simplifying assumptions. Okay, and in practice, what we are interested in is the following. So given samples drawn from the underlying distribution, PD, we would like to estimate the alpha star, right? So in the first few presentations we took in this series of reading group, we learned the restricted Boltzmann machines. So that is one class of unnormalized models. And there are lots of them, like language models, skip-gram models. So these this problem setting is quite ubiquitous in machine learning. So for example, let's consider, just to give you recall the difficulty of this problem, let's consider the simple model defined as follows. So let's suppose that we are given M feature functions f1 through fm, and we're going to define the log linear model as the exponential of the summation of alpha 1 f1x through alpha m fmx. Okay, so each alpha, the collection of these parameters, is going to characterize one specific, one specific unnormalized model. And if you want to do some parameter estimation with respect to this class, you need to, you often need to compute the normalizing constant of this unnormalized model. For example, if you would like to apply the maximum likelihood estimation principle, you are required to provide the normalization constant, because that assumes the normalizedness of the distribution for sure. And this is often hard to compute because in many cases we are considering the high dimensional X, right? So this is the motivation and the problem setting. Okay, so there are several existing solutions. So for example, we learned contrastive divergence in the context of restricted Boltzmann machine, but this also applies to any unnormalized models. But this requires the MCMC sampling, and it's not well understood in terms of what is the objective this contrastive divergence principle is optimizing and so on. That is quite not well understood. And there is another principle called score matching and so on. But in this talk, I'm going to talk about the noise contrastive estimations specifically. So this is an approach to estimate parameter of unnormalized models by optimization. And it can be interpreted as solving the unsupervised estimation problem by supervised method. So it's an unsupervised in the sense that there is no label whatsoever given the problem setting in the previous slide, but it somehow posits the problem in the form of supervised problem. So that's the interesting part. So the rest of the talk is gonna be in 3 parts. So in the first part, I'm gonna introduce noise contrast estimation and give you the supervised learning interpretation and like sketch why it makes sense. And in the second part, I'm gonna give you another layer of perspective with F divergences. And I hope this may give you another idea on why this is a good thing to do. And I will end the talk with some discussion, some open problems, like open questions, right? Okay, so is there any problem so far? I mean, is there any question so far?
Yeah, I came in a bit late, so sorry if I missed this, but what does it mean for the model to be unnormalized and why is that important?
Right, so if you recall the restricted Boltzmann machine, so that is an energy-based model. So each distribution is defined up to some normalization constant, right? So given a graph, you can compute the energy, and each energy defines.
Add up to 1 at the end, right?
Yes, yes.
Oh, yeah. Okay, all right, okay, cool. Okay, I get
right, it. Yeah, that is the Right.
All right, thanks.
Yeah. Okay. Any other question? Okay, so then let's proceed with the noise contrastive estimation. So before we introduce the noise contrastive estimation, I'm gonna do one preliminary thing. So I'm gonna introduce the scale augmented family in the following sense. So I'm gonna define phi tilde theta from phi alpha x. So this is the unnormalized version. And this phi tilde theta has another parameter c, which can be any arbitrary real value, positive real value. So what I'm doing here is that I'm extending the family by introducing another parameter c, so that this phi tilde, the extended family, can include value densities. So for example, if you choose c to be the x phi alpha dx, if you choose this c to be the inverse of the normalization constant of the phi alpha, then this c times phi alpha is a value density or value probability distribution, right? So in particular for data generating distribution, now there is gonna be theta star. So I assume that PDX, so there is some alpha star such that the normalized distribution, the normalized version of this is the PDX. So, and if we augment the scale here, then in this extended family, there is a parameter theta star, which is a pair of C star and alpha star that satisfies this. So this model is still well specified in a stronger sense, right? So we are gonna do the joint estimation of the parameter theta. So I'm gonna estimate alpha as well as C. right? As a byproduct, if successful, we can obtain the normalization constant 1 over C star from this approach. I mean, by augmenting this scale into the family. Right, so I'm gonna work on this phi tilde. Right. Yeah, so with this notion, let me first introduce a general approach of this noise contrastive estimation principle. So we are gonna do the estimation by optimization approach. So what I meant by that is, so we are gonna first design some objective function J theta such that the desired parameter theta star is the argmax of the J theta. So if you optimize J theta, then you can, so that you can recover the desired parameter. And given sample, what we are gonna do is that we are gonna use an unbiased estimator of J theta, which I'm gonna denote by J hat theta given the samples. And I'm gonna do the maximization. So I'm gonna optimize this unbiased estimator of J theta, and I'm gonna take that as my estimator given samples, right? And in practice, J hat theta n is often maximized by gradient-based methods. And this is not something very new. This is an old idea. So, for example, maximum likelihood estimation for normalized models can be understood in this framework in the following sense. So, for example, suppose that we are given a class of distribution P theta x, and the MLE approach takes the J theta to be the PD x Q, P theta x, so which is PDX log PDX over QX dx. And given samples, in practice, what we use is just replace this integral with the Monte Carlo approximation so that it becomes an unbiased estimator. So log PDXI. Sorry, so I should have used P theta here. P theta xi. And since when you maximize this with respect to theta, you don't need, okay, so I'm sorry. So I should have taken this to be minus. So maximization of this with respect to theta, if you consider this, then this PDXI, the underlying density evaluated at sample point is irrelevant to the optimization, so we can ignore this. You can just subtract this term. So this becomes the usual maximization of log likelihood, log P theta xi. Right, so yeah, so this is, here I just want to highlight that maximum MLE is also, can be formulated in this form. And NCE is another instantiation of this generic approach. Any questions so far? Okay, if not, let me introduce the NCE finally. So before I go into that, do you have any question? No? So before the introduction, let me recap the